Hello Year 12s, well done for getting this far. This is your final lesson of the summer term, and we're going to be finishing off Newton Raphson Method with its limitations. Here's your starter, all based on differentiation, and your answers. Right, so we met Newton Raphson Method last lesson, okay, and we derived it, and the brilliant thing about it, apart from the fact it's on your formula sheet, is that it is a very quick iteration. It finds the root very fast. You can keep going until you get the accuracy you want. However, if you don't choose your starting value sensibly, then you can have a method that fails to converge. It can be a disaster. So once in a while you're asked to choose a starting value, but that's usually straightforward and obvious. Okay, but quite often they would rather you explain why a choice does converge or why it doesn't converge. Let's have a look at an example. So this curve, perhaps it crosses the x-axis further along, but our starting value here is at a stationary point, a minimum value. If that happens, we know that the gradient at a stationary point is 0, and in our formula that means we're going to be dividing by 0, so we won't be able to find another estimate. Graphically, you know that the tangent at a stationary point is going to be horizontal, so it's parallel to the x-axis, so you're never going to have it crossing the x-axis and finding another value. So that one's a disaster. Another problem that we have is that you could get divergence. Okay, so here's an example, and we're going to see about when our starting value is going to oscillate either side of this root 0, but we're going to be diverging. So every time we're getting a little bit further away from that origin. These are some examples. I think it's good to see quite a lot so you can know what to look out for. So here we have a quadratic, and we can see that the roots we're aiming for are -1 and 2. But if we happen to pick 0.5 as our starting value, we have a minimum there, don't we? And so we know that we're going to have a tangent that's horizontal. We're never going to find the next value. But if instead we pick, say, 0.4, alright, then we do get the next estimate, but it's way off the screen, very far negative. So actually we started really close to -1, and we've now gone much further away. So our first iterate is further away than our starting value. However, that doesn't bother us in the long term, because if we continue this, we can see that each step takes us closer to that root. On the right hand side of the screen you can see here there are our approximations each time, so we're heading to the -1. And the same thing would happen if we tried, instead of 0.4, let's try 0.6. Okay, the same thing happens there. But what about if we tried a number that was much further away, a bit closer? So let's try let's try 1 instead. So if we try 1, we're ending up the same distance away, and then it's going to carry on closer and closer each time. Okay, so it really does affect how good our next estimate is, which one we start with. Let's have a look at another case. Okay, so here we can see that the only root that this graph has is at the origin, and the other bits here are asymptotes. Okay, and we can see that if we start with x is 1, in fact we're going to be diverging because it gets flatter and flatter, and where we cross the x-axis gets further and further away from the root every time. The same would happen if we started with -1 instead, or a more negative value, so we get further and further away. Okay, but what about if we started with 0.8? Okay, we're still going to get further away. Let's try and get the other side of that minimum. So the minimum looks like it's around 0.7. Let's try 0.4. Okay, so for 0.4 that looks pretty good. We're closer in. and we're closer in, and we're getting closer and closer and closer. And if we look on the right hand side of the screen at the values of our iterates, it's so close to 0 that we round to 0 after the fourth iterate. If we'd chosen instead 0.5, let's see what happens here. So I'll just put it back so you can follow it step by step. So we pick 0.5, there's our tangent, and that hits the x-axis at negative 0.5. Then if we take a tangent at negative 0.5, that hits the x-axis at 0.5. So we're back where we started. So in fact, we're just oscillating between 0.5 and negative 0.5, and we don't go anywhere. So things you need to watch out for these sort of questions. First of all, it's a good idea to check whether the gradient at the starting value is 0 or not. And then it's a good idea to sketch a graph to see what's going on and draw on some tangents. Here are some possibilities. You might have a turning point, which is the same as the gradient being 0. Or you're near a turning point. If you've got quite a flat gradient, then your tangent will be very far away for your next estimate. No matter what happens after that, it means that your first iterate is worse than your initial guess. And it may be that you converge back, or it could be that once you're past that turning point, you're going to be heading away from the route you're interested in, perhaps to a different route. The same could happen if you cross over a vertical asymptote. You could head away from the route you want and towards a different route or no route. You could end up oscillating, as we did. And the other thing to watch out for is if your function is not going to be defined for the value of x that you end up with after one iterate. It's also worth keeping an eye on whether the question is asking about what happens in the long term, convergence or divergence or oscillating, or whether it only wants to know about what's happening in the next step. So these questions only want to find out what's happening in the next step. Okay? And we want to also know about why that next step is not a better approximation to the root than the one we start with. So here's our function here. Now, the first thing I suggested for investigating was to differentiate at the point x is 1. We can make our calculators do that. So here's my calculator, and I want to differentiate. So I choose math and then d by dx, and I'm going to put in the function. So it was 2x cubed for this one, power, so minus 5x plus 2. And we want to work that out at our starting value of 1. There we go. So the gradient is 1. That doesn't ring any alarm bells, so that's super. So I've typed the function into my graph here and I've selected it. Let's see what happens when we draw it. Okay, I've adjusted these axes so you can see, but you might need to use view window. Your calculator can sketch a tangent, so I press sketch and then tang for tangent, and I want the tangent where x is 1. Okay, there we go, and we can see that we were actually quite close to the root originally, and now we're a bit further away as x is 2. Let me see what happens after that. So I want another tangent, but I'm going to clear this one so it doesn't look confusing. So if you press sketch and then CLS is clear the screen. There we go. And now I'm going to do sketch, tangent, and I'm going to put x as 2 in. So this will be my second iterate. I'm not asked about it, but I just want to see what happens. Yeah, so now we're coming back in towards that route. So it's not a long-term disaster, but my first step is further away. We can also use the calculator to find out the next value of the iterate. So if I go back into run mode, I want to do x, which was 1, my starting value is 1, minus the function using x in it, so it was 2x squared, so 2 times 1 cubed, sorry, minus 5 times 1 plus 2, divided by the gradient at 1. The gradient was just 1. That gives us the value of 2. Okay, so there was my gradient at the point. That's my working out if it's required. There's my graph, and I've drawn my tangent, and we can see that originally we were quite close to the root. We're now further away. So the problem with this is x1 is further from the root than x0. Here's my working out for my Newton Raphson formula. Okay, and I'm substituting in my starting value of 1 and I get a next value of 2. For the second question, we first of all work out the gradient at the starting value of 1. So this is my working out for differentiating. I'd had to use the quotient rule, but I could use my calculator. Alright, now I've substituted in 1 and I get 0.07. So that's fine, it's not 0. And now we could use the calculator to sketch the graph, and you might need to adjust the view window, and then we press sketch and tangent and type in 1 to get our tangent there. We can see it's way off here. And the big thing is we've got this massive empty area. Okay, so the function is not defined here. It makes sense. It involves a log of 2x, so the function is not going to be defined when x is less than 0. So no more further iterations are possible. After we found that first one, which turns out to be negative 4.52, then we can't do any more. This hopefully would just be a find question where you could make your calculator do all that working out for you. You have a go now. Here's your first equation, starting value 1. There's the gradient. There's the next iterate. There's the graph, and you can see you started pretty close to the root. You're now further away from the root. So that's the problem. And the next one, there's your gradient at the point. Okay, on this graph here, so we've sketched the graph and we've drawn the tangent. And you'll notice because of the it's kind of related to the tan graph, you've got an asymptote there. Now your tangent has crossed that asymptote, so actually you're now closer to a different root instead of the original one. That estimate, your next iterate is 3.70. Right, in this question we have a nice quartic, and we start off by showing that we've got a root between 2 and 3. Remember, we use the sign change rule for that. So evaluate this, I'm going to call this f of x, and evaluate it at 2 and 3. And notice we have a less than 0 and a greater than 0, so by the sign change rule, there must be at least one root between 2 and 3. Okay, for this next bit, we're looking at why is 2.5 not a suitable starting value. So we're going to check first of all the gradient at 2.5. So I'm going to differentiate and pop in 2.5 and we get 0. So that means we have a stationary point. We've got two ways of explaining this. Either thinking about we would have to put a 0 into the formula and we can't divide by 0. So we have an undefined next term. Or you can think graphically. There would be a tangent would be horizontal at this value. Okay, and so we would never cross the x-axis and never find any further estimates. For this example, okay, we are told that we have a root between 0.5 and 2, and we've got to find out why the Newton Raphson method doesn't work with 1.5 as our starting value. So it makes sense to differentiate and pop in 1.5. Now we're going to have to use the quotient rule for that. But if the question doesn't direct you to show detailed reasoning, you can just use your calculator in math and d by dx in run mode. However, this is the working out if you need it. So we've got v du by dx minus, so that was v, that's du by dx, minus u, is that bit, dv by dx, all over v squared, and then tidied up. And substitute in 1.5. And it turns out to give us negative 0.8. Now why is this a problem? Well, if we look at the original function, we'd be trying to find a log of negative 0.8 when we pop it into our Newton Raphson formula, let's see. Okay, so we'd have to put in the negative 0.8 into the function. It doesn't work. So it's undefined for x is less than 0, so we can't find the next value. And you can see it graphically here. Your tangent's taken you past into the x less than 0 zone, and so you can't find the next value. Here's an old exam question. So we're given a cubic, and we know it's got 3 roots, one of which is positive. Here's a sketch of the graph down here. First of all, we have to show the Newton Raphson method gives us this. Now we know the Newton Raphson method is not one single fraction, so we're going to have to do a bit of substituting and simplifying. Here we go. So first of all, there's the Newton Raphson formula, and we just pop in our function, which was this cubic, and we differentiate it for the denominator. So we now need to make a single fraction, so we're going to have a common denominator of 9x squared plus 10x minus 1. Multiply the x, top and bottom, by that. Okay, and I've used brackets here because I'm subtracting, so I don't mess up with the signs. Then very carefully expand and simplify, and we end up with the thing we were aiming for. Good news. Okay, for the second part, we're going to apply the iterative formula for a starting value of -1 and then see what happens, illustrating on our graph here. Okay, let's see what happens on the graph. So we start with x is -1, we go up to the curve, we draw our tangent, and it hits at 0. And then from 0 we go down, and then we draw a tangent, and it takes us back to -1, and we're going to keep repeating that. So we're oscillating. Now, I think it would have been a bit difficult to just draw that by hand graphically. You wouldn't know that's exactly where it goes. So there are 2 things available. You can use your calculator to do those sketches, and it will show you, but you can't kind of trace for a tangent. Or you can just work out your next 2 values. So you put in -1 into this formula from part 1, and you get 0 out, and then you put 0 into this formula and you get -1 out. Okay, that's the mark scheme there. Here we are given another graph of a cubic, and we have 3 roots, alpha, beta and gamma, and we are told that we have turning points at x is 1 and x is 2. And what we're expected to do is investigate what roots we go to with different starting values. So they're saying the starting value is called k. So for the first one, we want to find out what happens if k is negative. So a starting value is negative. So we can see that when we draw a tangent, we end up in the positive zone and we are heading towards alpha. Okay, the next time, what happens when k is 1? Well, we're told that we have a turning point at 1, so we know this is parallel to the x-axis. There will be no further iterates, and so no solution. And then we're going to look at what happens in between 1 and 2. So let's try really close to 1. Okay, so I can follow this green line to where it cuts the x-axis, and it's now to the right of gamma. If I now draw tangents from there, I'm going to be gradually travelling towards the root gamma. Okay, what about if I try closer to 2? So this is really close to 2, so about here, and this time we're going to be hitting the x-axis close to alpha, so we're going to reach alpha. And then somewhere in between, we're heading for beta. So in fact, what happens if k is between 1 and 2? We can't tell. It's impossible to say because it could go to any of the 3 roots. Here are some questions from the textbook for you to try. The answers. And some more questions. And here is the last one from that exercise. And then this is from the mixed practice. So this is an interesting application of your trig that you learnt at the start of year 13 work. And here are the answers, and I'll show you some method. So that's the method for question 2 and the method for question 6. Now these are extension questions. Okay, and here are the answers. Here's the method for number 8 and the method for number 9. Here's question 10, definitely an extension question. And here is the method. Okay, and a final extension question. So you don't need to do those extension questions unless you want a real challenge and you've got some time. Well, I hope you have a wonderful summer. You have made it to the end. Fantastic work.